Chapter 12 is really looking at addition reactions, but with cyclic intermediates. So that's our primary distinction. In Chapter 11, it was all about forming a carbocation. So everything that determined what product formed or what reagent reacted was all about carbocation stabilities. When we move into Chapter 12, we end up forming these very weird cyclic structures. And in most cases, they are extremely stressed structures where you've got three-membered rings. Right? At the very tail end of Chapter 4 or 12, we run it into a four-membered ring, transition state at least. Okay? So that's kind of the important aspect to remember with each of these. So we've got our nice general summary here of everything that's happening. With our Chapter 11, we just had the acid go through to activate it. When we move into Chapter 12, that's where things get a little bit sticky as far as our intermediates. In most cases, what we end up forming is some kind of bizarre three-membered ring. Okay? So the reaction occurs by your pi bond coming out, reacting with the electrophile, and forming this three-membered ring. What makes most of these reactions super reactive at this point is that electrophile almost always stays positive. Okay? That positive charge means that we now have an exceptionally good leaving group. Okay? Can't act very well as an electrophile because it's already, we'll find they've already satisfied their octets. So now that we have a great leaving group, we're either looking at breaking that bond or that bond, but the thing that's going to force it out will be your nucleophile. So your nucleophile can potentially come in and attack either of those carbons, pushing out the electrophile. Okay, so you've got two possible attacks or directional attacks once you've formed this three-membered ring. Okay, so each of these mechanisms starts to evaluate which of those positions is favored in the breaking open of the structure. Okay. Before we take it too much further, we're going to talk about some nomenclature here, or sort of nomenclature. So if we take a look at our pi bond, or our alkene, what I've done is tried to show the p orbitals. So really, to further accentuate this, what we can go through and do is add wedges and dashes. So that we can see those pi bonds a little bit cleaner. Okay. At this point, X and Y can potentially form bonds to our pi system. We could start to link up our X and we could start to link up our Y, and then go through and erase bonds, okay, and have all sorts of fun products coming out of this. Okay. The important aspect here is that if it links in this fashion, what we've done is we've put X and Y on the same side of our pi system. Does that have to be the case? No, it could be possible that instead of linking them on the same side, we're linking, in a very goofy looking system, to the other side. Okay. So this drawing kind of shows the similarities between these. Okay. So in that top case, they attacked on opposite sides. And in the bottom case, they attacked on the same side. So what would drive one reaction over the other? Any ideas? So it could have something to do with the strength of the nucleophile. So we would see a result. So how would we visualize that this was necessarily something happening? We would see that through optical activity. Okay, so optical activity is a good way to phrase this question then. Which of the products is optically active? Okay, or which product is optically active? Depending on our mechanism, we may get a different answer. Okay, but that doesn't explain why we're saying one versus the other. Okay, so we looked at one option being the strength of our nucleophile. It's an interesting idea. If our Y was our nucleophile and X was our electrophile, how might that affect our reaction? There is no right answer in this case.
Well, the Y could be drawn to where there's fewer electrons to the opposite, right? While the X goes around the other side.
So our pi bond's going to initially shift the electrons outwards.
Mm-hmm.
Okay? What's going to be the problem if those electrons come out of the structure? What are they going to start to push away? They're going to start to push away the Y, okay? Which means the Y can't come in at the exact same time. Okay? So what might allow it to come in at the same time? Has something to do potentially with size. We're looking at some kind of steric effect, shifting things around. If it's bigger, if anything, that's going to push the Y further out of the way, and we're now going to open up the possibilities for this opposite and same side. Opposite and same side, as we've seen already with our nomenclature, with alkene nomenclature, is too general of a term. So we end up referring to these products according to their relationships of X and Y. So instead of being opposite and same, we could call it, we could try cis and trans. But what's the problem with that? Cis and trans is in reference to a double bond or a ring where you can't do rotation. Both of these structures, we can do rotation. So cis and trans doesn't quite work. Okay, so it's not a bad idea for understanding the results that they came in on opposite sides or the same side, but they pick up a different name. Right? What we refer to are our syn and anti additions. So that is our anti product, and this is our syn product. Okay. What we're referencing is the action itself, not necessarily the products. So to get that top product, we went through and did an anti-addition. What that's meaning is that the way the alkene reacted with our electrophile and nucleophiles, they came in on opposite sides, okay, or anti to each other with respect to the pi system. Okay, so we've got our electrophile on one side and our nucleophile, coming in on the other. So that's ultimately what's happening in our anti-product. Okay. In our syn product, what's happening? They're coming in from the same side. Okay. So when referring to the anti and syn systems, those are adverbs because they're acting on the action of the addition. Okay. If we refer to cis and trans, those are adjectives because they're acting on the actual structure, okay, a noun, if you will. Okay. So it's kind of the relationship. You're getting at the same idea, just slightly different parallels, okay, within it. So we will be referring to our products as anti-products or syn products, potentially. Okay. I'm not a big fan of nomenclature, so you'll typically not hear me reference these terms, but it does show up in the textbook, and it's important to understand the chemistry around where your groups are located. Okay. Questions on that? So our ring transition states. Alkenes kind of have an interesting reactivity. Because of this pi system, okay, and that nonpolar pi bond, we really have kind of a partial positive and a partial negative to it. So two carbons are active. Okay? One is our electrophile, one is a nucleophile. This chemistry gets kind of bizarre and allows for all sorts of kind of interesting reactions coming out of it. Okay? Much less so than if we made it a polar pi bond, because now we strictly, we've polarized it too far that we don't get the same type of chemistry. We have a very clear electrophile and a very clear nucleophile. Okay. There does happen to be an example of another system that has this same kind of reactivity. Okay. And that reactivity comes down to a single atom, which is even more bizarre. Okay. We have the possibility for an atom to act as both an electrophile and a nucleophile. Seems a little bit puzzling. Why would that be weird? How can I take a single atom, so here's my atom, to have it act as an electrophile, what does it need? It needs a positive charge. Okay, to be a positive charge, what do we have? Lack of electrons. We're starting to push into something that looks like a p orbital. Okay, so there's a reasonable electrophile. But we're saying the same atom can potentially act as a nucleophile. What does a nucleophile need? It needs a negative charge. It needs a source of electrons. How can I get an atom to act as both an electrophile and a nucleophile? Okay. We can push to larger atoms. Larger atoms work fairly well as electrophiles and nucleophiles. Because they are so large, they are very polarizable, which means the electron cloud can shift to one side of the molecule. If it shifts to one side of the molecule or one side of the atom, the nucleus becomes exposed, and that side of the atom looks very positive, and the other side of the atom looks very negative. Okay? So it's kind of a bizarre system, but that ends up being what happens. Okay? In one particular case that seems even more interesting is we can put on our lone pair and we've got our nucleophile. Okay, so a large atom works very well at this ability. Okay, so we can look at standard characteristics. Large atoms are good. What other atoms might be good? Electronegative is not going to quite work. It still kind of goes hand in hand with our large atoms. That's still with our large atoms. Metals also tend to be pretty good at this. Why would a metal be pretty good at this? Where are a lot of our metals? In our fourth energy level, which means they are relatively large. Take it a step further, what do those large atoms typically have associated with them?
Empty shells.
Positive charges. They have d orbitals with multiple oxidation states. Those d orbitals can facilitate the acceptance of electrons or the release of electrons. Okay, so our large atoms and sometimes our metals can mess with this and do this weird, bizarre chemistry. Okay. So after looking at these possible atoms, now let's look at a more particular case. Turns out that carbon can also do this chemistry, which seems very counterintuitive. Why is that a problem? Carbon is not large and it's also not a metal. We have no d orbitals. So it seems really odd that we can get carbon to go through and do this system. Okay. These molecules tend to be very, very reactive. What we're looking at is something known as carbenes. Okay. They show up fairly rarely, but you can see them pop up every so often. The two most common ones are diazomethanes and trihalomethanes. Okay. We'll look at the formation for both of these. Okay. So the diazo. In a diazo system, what we end up having, let's see if I can draw this appropriately shaped. Whoops. There's our diazomethane structure. So the diazo is in reference to the two nitrogens. Okay, azo is really our signifier for nitrogens. Okay. Why is it methane? I only see two hydrogens out here. Why do we call it methane? It's only one carbon. They're also calling it an ane and not an ene. It looks kind of like it has a double bond. Why do we not reference it as the alkene? Oops, let's not even draw that yet. What have I just drawn? Drawing a resonance structure, and it's likely this resonance structure where a large part of the name is coming in. Okay? In this case, we don't have an alkene, we don't have a pi carbon. We have an sp3 carbon still with that negative charge. Okay, so it doesn't really make sense to reference it as the alkene. What becomes interesting about this molecule? As far as reactivity goes, what do you see? So reactive, good call. It is exceptionally reactive. Diazomethanes are so reactive that in fact they are explosive. Right? If you go back into our labs, take a look at all the joints, the glassware that we have. All of that glassware has frosted glass so that we form a nice tight seal with our glassware. When working with diazomethanes, you cannot have frosted glass because the frosted glass provides a nucleation point whereby you can cause the diazomethane product to explode. So in general, not a good compound to work with because they are very explosive. Those that have worked with them usually have the cuts and scars and missing fingers to prove it. Okay? So they are very, very, very reactive. What makes them reactive? So we do have the positive and negative charge in the same molecule, so we could refer to this as a Zwitter ion because it's got both ions. It's a twin ion. It's a little bit more than that, though.
That's because the carbon is negative and the nitrogen is positive, and the nitrogen is more electronegative than carbon.
So we could look at that difference in electronegativity, saying the nitrogen does not want to be positive. So what does it want to do?
Steal the electron.
Steal the electrons from carbon. If the nitrogen takes the electrons, what happened to the carbon? So it does officially become neutral, but it's a bit odd. Why would it be a bit odd? So that compound is officially neutral. What's its hybridization?
sp3. Or
It is not sp3, it is sp2, which means what does it have? It's missing its octet, which is going to make it very reactive. But because of that missing octet, it has an empty, unhybridized p orbital. What can you put into that p orbital? Electrons, say from our alkene. So the alkene can donate electrons up to the carbon, which then kicks out that other molecule as what molecule is that?
N2.
Nitrogen gas. Why might this reaction be incredibly favorable?
It's very stable.
Nitrogen gas is ridiculously stable. In fact, it's pumped into a lot of reactions as an inert atmosphere, so we can maintain a pressure on it, but not introduce reactive oxygen. Okay, so nitrogen being exceptionally stable as a product now really pushes this reactivity further along. Okay, but if we did just that single arrow pushing, what happens to the other carbon? We'd have a carbocation. Okay? A carbocation right next to a giant source of electrons from that carbon. What ends up happening? The electrons immediately cycle back down. The result we get, whoops, try and include all of our bonds here appropriately. A cyclopropane. Okay. And we might say that this is an extremely stressed structure and this would never actually occur. Why does it potentially occur? Well, it goes back to what our other byproducts are. Nitrogen being exceptionally stable. Okay, so taking a high energy starting material, we're now forming a very low energy product with our nitrogen gas. We end up overcoming that cyclopropyl energy, and we can actually form it. Kind of a neat little reagent. Questions on that?
So I was thinking the carbon that you lone pair, the lone pair of electrons,
Mhm.
When it gets close to that pi bond with that 2 electrons, I was thinking there's going to be a repulsion or something there. Like a 2 electron.
So what you could end up doing is looking at a pseudo-repulsion of those electrons, pushing it to the other end of the carbon molecule, or the other end of the carbon atom, which then allows it further to cyclize. Okay. More than likely, you're probably looking at something a little bit more along these lines. Our carbon with the empty p orbital. And then we would have our lone pair and our hydrogens. So the electrons from our pi system can shift up into that p orbital. And our lone pair, which I know isn't officially a bond, but that's kind of what that's showing, can coordinate down into the empty p orbital of the pi bond. All right. So we end up forming a cyclopropane structure. Kind of neat, sort of bizarre, interesting chemistry. Questions on that?
That's just the diazo.
That is just the diazomethane compound. Right. So ultimately all you're doing is forming that cyclopropyl structure using a diazomethane. We formed a 3-membered transition state, okay, which turned into a 3-membered final product. Okay. What's a problem potentially with this 3-membered product? Not really a problem, I guess.
Some carbenes.
There's a lot of sterics in that. That ring does want to bust open, but what makes it problematic for it to bust open? There's no leaving groups. There's no polarity within that. Okay. That structure on its own is actually going to stay pretty much stuck. Okay. We end up with the cyclopropyl until we change the chemistry by bringing in some other leaving groups or something to polarize that carbon structure. You're pretty much stuck with that. Okay. Questions?
It's just kind of swapping lone pairs.
Yep.
From the top to the bottom. So like, why doesn't it just take the lone pair that it has and keep it on?
If it just takes the lone, sorry, run that by
So
me
you
again.
got like a lone pair on the bottom, like I guess hanging out, right? And then it takes a lone pair from down at the bottom up into the empty p orbital.
Mm-hmm.
Why doesn't it just take its other lone pairs, or are they already in the p orbital?
Interesting question. I think what you're getting at is that if we look at that structure for our carbene, we can't actually have that be a bond for our lone pair, but that's ultimately what we're looking at for our carbene, right? Why can't that lone pair just shuttle into that p orbital?
Yes.
Any ideas?
You're going to have another empty shell, and the p
So-
orbital is the highest.
Number one, you're going to end up emptying an orbital that you're going to need to explain. So that's going to be a problem. There's another big issue. We erase the diazomethane. What product do we get in this reaction?
The chlorine and then the attack.
So one suggestion was, which would be what type of reaction? Substitution. According to what mechanism? SN2. Let's try that. Where's the backside of that carbon-chlorine bond?
There's not one.
What's on the backside of that carbon-chlorine bond? Electron density. So in an SN2 reaction, what does that nucleophile with all its electrons have to do? Go through all of that electron density. Is that going to happen? No. So SN2's out the door. Sorry. Not a bad idea, but it didn't work. So no SN2. So then the next option is, of course, well, let's try SN1 then. SN1 happens, leaving group leaves, and we end up with this structure, right?
Which you can't do because you'd have the charge on the pipe.
that structure doesn't form. One of the reasons that students like to use for why this structure could form is resonance. There is no resonance for this structure because
You'd still have a pi bond.
orthogonal orbitals. The pi system is in p orbitals coming in and out of the plane at you. Where is the p orbital for that carbocation?
There is
It's in the plane of the paper. If you've got electrons in opposite orbitals, so in and out of the plane versus in the plane, you cannot share electrons because
It's not the same.
They're not splitting.
zero overlap. Why can the electrons in the carbene not just jump up to the p or the pi orbital? Zero overlap between those orbitals. Okay? There is no way for the electrons to jump up into that pi system. Okay? So instead, we just get a crazy, weird reactive species. Other possibilities coming out of your trihalomethanes. Okay, or bromine, doesn't really matter. Works even better with your fluorines. So your trihalomethanes, we look at this. Remember, we're still aiming for that negatively charged carbon and that positively charged carbon. Okay. How could we possibly generate that from this structure? Evaluate the bonds. Bond between carbon and chlorine. Is that a polar bond? Absolutely. Where are those electrons being drawn? Towards the chlorine. So would we ever predict chlorine to be able to, or sorry, carbon to take electrons from the chlorine? No, doesn't happen. But what could the chlorine do? It could take the electrons, making the carbon positive. What did we just find? Our electrophile. There's our positively charged carbon. Okay. But we still need the nucleophile. To get the nucleophile, the carbon has to take electrons from something. If it can't take them from the chlorines, where does it have to take them from? Oh, man. Yeah, highly unfortunate. It could potentially take them, whoa, I don't know why I wrote Cl, from the hydrogen. Anybody have any problems with carbon taking electrons from hydrogen?
There's similar charge.
Similar
Or
electronegativities. There's no reason for the carbon to take those electrons away from the hydrogen, except
What's the covalent shell?
what's the problem with carbon right now? Why is it partially positive? There's a strong inductive effect pulling electron density away from the carbon. That makes that carbon effectively more electronegative, trying to suck electrons from the hydrogen. Okay? Still not a favorable reaction, but what could we do to help facilitate that? We need something to take the hydrogen. What would that something be? A strong base. So if we now add a strong base into our system, what ends up happening is that that carbon can take the electrons ultimately away. We form the lone pair. What will end up happening is our, what is that species? Our alkene can come in, attack the carbon. We've got the chlorine as a leaving group. The lone pair on the carbon can come back in. What do we end up with for our product? Two chlorines. All right. Still going through a carbene intermediate. One of the things that's also going to help drive this reaction, you form chloride. Chloride is now a nice stable molecule. Another thing that could potentially help with this, these halogens are fairly large, which means what are they going to do to the bond angle? What are they going to do? they're going to constrict it because those chlorines are going to want to fill up space, which means those other carbons are going to have to kind of constrict away from it, which is going to help facilitate closing that cyclopropane ring. Okay. Both cases, we have a way to form carbenes. Are there other methods? Yes. Do those other methods potentially show up? Yeah. Just kind of look for these. What you're looking for is a carbon that can act as both an electrophile and a nucleophile. So evaluate the reagents you have and see what you can do with it.
Wouldn't it be harder for this to like work with bromine or iodine?
Both bromine and iodine are going to be even bigger, which are going to take up even more space, which is going to constrict that bond angle even further for your cyclopropane. We would expect them to be a little bit more difficult to go through and run because they're less electronegative than your chlorine. Okay. But they also work.
Any other strong base, which is like NOH minus,
Mm-hmm.
would that just react
With your, go ahead, finish it.
wouldn't it just react instead of the chlorine not becoming, the carbon then becoming negative and then, or having the lone pairs and then react with the product, with the product?
Which product?
The
So you're saying our strong base, so let's go ahead and say we've got our strong base of OH minus.
yeah.
What are you referencing with that OH minus?
So when the OH minus react instead of the
Sorry, I didn't hear that over the cough.
when does that OH minus react with the reactant versus the trimethylhalene?
Would the OH minus react with the alkene?
Yeah. Wouldn't that just react with it? It's already legally charged.
What does the alkene act as first? A nucleophile, an electron donor. Okay. What happens when that electron donor gets near another electron donor? Repulsion. So that OH minus cannot attack the alkene. That attack is not valid. It's supposed to be an X. Okay. Because there is no positive charge on the alkene. The only way we can start to form that positive charge is if we can polarize that pi system by adding in, say, an acid or an electrophile. Until that's happened, you can't have it act as an electrophile.
So why can't it react with the carbon?
Why can't it react with what carbon?
The one that,
Oh, up here?
yeah.
Quite likely it could, but it's also not going to stabilize that lone pair. So the only thing that would stabilize, and actually it's going to have a, oh no, it could do that. Okay, it could go through and react, but then you still have the lone pair on the carbon. There's nothing to stabilize that. So you'd end up forming a very reactive structure, a very reactive product. The only thing that neutralizes the carbene reactivity is something that can react with it twice, both an electrophile and a nucleophile. The alkene satisfies that.
So you have like OH and you just, that hydrogen coming off the carbon and you just want water. Most likely.
Yeah. Typically, you're using a stronger base than OH minus. It's usually T-butoxide. So the reason I mention this, just because I'm teaching biochem and the biochemists seem to think that organic chemistry doesn't show up. So here's a nice little tangent. Anybody recognize this? Yeah, it's the Krebs cycle. Okay, right up here at the very top of the Krebs cycle, fun little reactions occurring using the enzyme pyruvate dehydrogenase, okay, which you may or may not remember from any biology classes. And we get this fun little diagram of all these different things exchanging and moving around. Okay, the one that I really want to draw your attention to is this intermediate stage here. Okay, and in particular, thiamine pyrophosphate. Thiamine pyrophosphate is an interesting cofactor when you're looking at the biochemical reaction. Why is it interesting? If we take a look at its structure, if I remove the hydrogen, that carbon then becomes negatively charged with a lone pair. What is special about that carbon? It's reactive as a negative charge, but if we look at the nitrogen that it's bound to, that nitrogen is positively charged. What's the resonance structure? The resonance structure forms a carbene. thiamine pyrophosphate is a carbene. Okay? It is a naturally occurring stable carbene. Okay? Kind of a fascinating topic, if you ask me. We're looking at this molecule that looks insanely reactive that we would never expect to exist in nature with our standard carbenes, and yet, what can happen? Nature also forms carbenes, which becomes useful in that reaction. So if we moved into all the way strictly into biochem, you're taking pyruvate dehydrogenase. What you end up doing is you convert a molecule of pyruvate all the way down to acetyl-CoA, which I know doesn't show up on our screens. Okay? Through that big, long, nasty mechanism. What's a particular fun aspect of biochem? Think back to your biology class. Everybody's, or have people taken biology where you talked about Krebs cycle. Pyruvate dehydrogenase as a name, did that come out? I'm a little sketched on what gets revealed in biology, so I don't know. Okay. Just pyruvate. So one of the things that gets added into biochem is what are all the enzymes, what things are actually going through and doing this. And depending on what they decide to reveal in biology, maybe they tell you about it or not. This big, long mechanism that you see drawn here is one stage of the enzyme. Okay? Officially, this chemistry is something that you will be responsible for at the end of second semester. You got all sorts of nasty things going on and occurring through it. And in biochem, officially, that's what you should be doing, is you're looking at how those molecules change their structure from, say, pyruvate to acetyl-CoA. What's occurring in each of those steps? Well, typically when we talk about this in biology, this is what you see. Why? They don't care about the chemical aspects of it as long as it gets done. Okay? When you move to biochem, having a solid understanding of how the electrons move can then remove this memorization aspect and can put you in a situation where you can predict how the reaction is going to occur and what's going to happen within it. What makes biochem kind of frustrating is all that information gets washed away, right? And ultimately what we end up saying is a nice fun conclusion. The enzyme does it. So if you want something done, all you got to say is the enzyme does it. Okay? Just like in organic chem where we said the answer was resonance, in biochem the answer is the enzyme does it.
Yeah, protein.
Proteins are enzymes,
Oh, yeah.
and vice versa sometimes. Okay. So that was our nice little fun tangent into natural forming carbenes. Kind of a fun system to look at. I would have recommend that you go back and take a look at that mechanism and see how it actually functions. I think it's actually kind of neat. So then the next part of this, which is probably the more important part, is how our alkene can act strictly as a nucleophile. Okay? And this is in the case with not obvious electrophiles. I know it seems a bit odd, but that's how our textbook has organized it. Okay, what do I mean by not obvious electrophiles? Well, if we take a look at that first reaction, Br2 and DCM. Number one, DCM. What is DCM? Dichloromethane. It is a solvent. Okay. So sometimes you'll see it written there, sometimes you won't. What is its role in this reaction? Dissolve stuff. And that is it. Okay. So if you're seeing the abbreviation DCM or even DMSO, some of those kind of acronym switches out for your polar aprotic solvents, they're really there just as a solvent to keep everything dissolved. You can kind of ignore it. What you can't ignore is when you move to the protic solvents. The protic solvents have an issue. What is the issue with your protic solvents? They can donate hydrogens, and they also often act as weak nucleophiles because they can ditch the hydrogen later on because of that protic aspect. Okay, and we'll see that pop up with this. So, in that first reaction, we said DCM as our solvent. What does that mean Br2 must be acting as? Acting as what? Okay, our electrophile, and as we're kind of alluding to with our carbene, also as a nucleophile. Okay, so the nucleophile aspect we may be okay with. Why might we be okay with the nucleophile aspect of bromine? We got a lot of lone pairs within the structure. Okay. So that could explain the nucleophilic characteristics of it. However, for it to act as a nucleophile, it would exceed, it would exceed the standard number of bonds that we're used to seeing, and that seems a bit questionable. Okay? So having it act as a nucleophile first is probably not a good option. Okay? So what we're saying is that it has to act as an electrophile in this case. How can it act as an electrophile?
The electrons from the bond shift to the one end.
Bromine is a very electronegative element. So what we can do is take the electrons in that bond and push them towards one end of the structure. What happens to that first bromine? It starts to become positively charged. Okay? So we need something to stabilize that positive charge. What do we have? We have a pi bond in the alkene, which can share its electrons with that bromine. Okay? And our kind of standard approach to our reaction, so please don't draw this part of it, we might go through and say we end up with something along these lines, with our positive charge on our carbon, so we've got our carbocation. Very similar mechanistically towards what? Not SN1, it's not substitution because we did an addition. Okay, and push it further, I think you actually even added the detail to it. It's an electrophilic addition. Okay. This electrophilic addition should look really similar to the mechanisms we've already done in chapter 11. Okay. Just a straight electrophile addition. What's the big primary difference in this addition versus the addition we did in chapter 11?
Because you're adding both bromines.
Nope, we have not added both of the bromines. Push that a little bit further, Will. What do you mean by hydrogen?
It's not a hydrogen.
It's not hydrogen. We're adding hydrogen in chapter 11 versus adding bromine in chapter 12. What is the difference between hydrogen and bromine? A lot. That's helpful.
Bromine's much larger.
Bromine is much, much larger. Not only is it much larger, it also has more electrons. One of the things why it's bigger. Hydrogen, once we put a hydrogen on, does not have any electrons. It cannot act as a nucleophile because it is now out of electrons. Bromine, on the other hand, can donate electrons. Okay? So instead of forming that carbocation intermediate, what ends up happening is that bromine immediately shares its electrons back down. The result is that we end up with a positively charged bromine. Anybody have problems with a positively charged bromine? Yes. So we might immediately say, well, this mechanism is a load of crap. There's no way it could possibly work. Okay? The reason we know or we assume that this mechanism works better than showing the carbocation is if we form the carbocation, give me a sec, we'll come back to that. Okay? Once we've got these products, okay, both of them are unstable. Does everybody agree with that? Yes. Okay? So what would happen to stabilize them? The other bromide can come in and attack our positive charge. So let's be a little bit careful. So the top one, black one, is okay to look at. The purple one's got a little bit of problems. What's the issue with the purple one? I'm going to come back to that stereochemistry issue in a second. In our black one, we had the bromide attack what? Positively charged carbon. Can we have the bromide in our purple one attack the positive atom?
No.
Why not?
It would exceed its octet.
Exceeds the octet. Okay, so it's not just finding the positive charge, it's finding the most reactive positive charge. That positively charged bromine cannot accept more electrons. So what does it do?
It steals
It steals electrons that it already currently has. Problem with that? We'd form a carbocation. We said we can't form a carbocation. So how do we fix this mechanism to show that we don't form a carbocation? The other bromide can come in and attack at the same time, and we end up with a product. Now back to your statement, Jimmy. The difference between these products currently is nothing. Okay. What is an issue with both of these products? What do you mean the positioning of the bromides? I agree.
They're too close to each other.
Not quite that. The spatial relationship between the bromides, the stereochemistry. If we take a look in the purple case, the bromide, or our first bromine, formed that effectively cyclopropyl structure with two stereocenters. Both those carbons are stereocenters. So let's go through and say that our pi bond reacted upwards. What does that say about our other stereocenter? That bromine bond also has to be upwards. There's no way else I could do that, which means the methyl group is dashed. Which means when I get to the product, or now when I go to the product, what do I see? So this bromine, I didn't change that bond. What happened with the other bond? Becomes dashed. Why is it now dashed? Backside attack. What is the relationship between the bromines? Trans, which I'm going to put in air quotes.
Anti.
We did an anti-addition. Son of a... Don't put your head down. You didn't erase it all. What did we say? Anti-addition, trans, air quotes. What happened with the black one? In that first intermediate, how many stereocenters do we have? Only one. So let's again run the assumption that our bond formed upwards. If we now look at our product, what happens?
You can have anti or sin.
You end up with that new bromine potentially being anti or potentially being syn. Why both?
Because it doesn't do backside attack.
Why can it go to the top or the bottom? What is the bromide reacting with? A positive charge on carbon. What orbital is it reacting with? A p orbital, which has above and below empty space to dump electrons. That bromide can attack both above and below. We end up with two possible products. How do we know that the black mechanism does not work? Because someone went into the lab and tested it. What did they discover?
It forms
No syn product forms. The only way or the only explanation we can come up with to show that the syn does not work is is by going through that other mechanism where we form that cyclopropyl propane type intermediate.
So with that reaction as it is, would the syn wouldn't have or it would have optical activity, that's how you would check it?
We don't want to bring optical activity into this argument at this point. We can talk about the experimental evidence later. Okay. So the result is that we end up forming that cyclopropyl type intermediate, much the same way as we did with our diazomethane, okay, forming our carbenes. That intermediate is most commonly referred to as a bromonium. Why bromonium? Because it's a bromine atom and it's positively charged. You'll find that when we look at positively charged atoms, we almost always add this ium on the end of it. NH4 plus is ammonium. Okay. So that ium is supposed to give you kind of a hint that you're looking at a positively charged bromine. Okay. So let me draw that intermediate a little bit cleaner here. Is there another issue that pops up with this? How many products do we expect? We might say just one. Why would you say just one? Because I can't form the syn product. Does that prevent me from forming another product?
No.
No. What's the other product?
Same thing, they're just wet.
Our initial bromine, whoops, I didn't mean to draw the product again. Our initial bromonium ion could have formed below the plane of the structure. Okay. Which means we end up with two possible products. Okay, so you have to be aware of that. Why do we have two possible products? How many stereocenters are in your starting material? In your starting material? 0. It is an achiral molecule, which means your product must also be achiral. If we draw only one product, is that product achiral? No, it is optically active. The only way we can get an achiral product is we end up with two products, so that our optical activity cancels out. Okay? Oh, good. And I lost a connection. That makes this even better. In our second step, we had the bromide come in and attack. Where did the bromide attack? Backside. Take it further. Was it just the backside?
No, the p orbital.
There is no p orbital, officially.
In the same plane as the other
Opposite chiral center.
It is attacking a chiral center, and it is backside attack. That's an awful long red curved arrow to show. I wish I could have shown something shorter. Say like that. But that does not happen. Okay. How do we know that doesn't happen?
Because it would form a difference between the tertiary and secondary.
So it is a difference between the tertiary versus the secondary. In this type of reaction, we're saying that that happens at what? Same time or different times? Same time, which suggests what mechanism? SN2. SN2 favors strong nucleophile, check, and a primary or secondary substrate. So according to our SN2 dynamics, we would have expected the bromide to attack the other carbon. How do we know it didn't attack the other carbon?
Because the other bromide was there.
We have to test it. We have to go in and prove it. Okay. With bromine and bromine, are we going to be able to tell much of a difference? No. So what do we end up doing? Something else? Good call. our electrophile came from Br2. I have to use Br2. There is no other choice. Okay. But what happened in the second step? We're saying the leftover bromide attacked. That bromide is acting as? Is it possible to generate a different nucleophile? By, say, maybe adding water? Is that an experiment that's allowed to happen? Yeah. All I've done is I've changed the solvent. By changing the solvent, I can now change the dynamics of this reaction. The changing of that solvent now allows me to see a difference between those two positions. Okay. What ends up happening when I go through and use water? What do I see? Whoa. The water attacks here. How do I know it attacks there? You did the experiment and you proved it. The dynamics of this reaction are coming out of the lab, not out of somebody just sitting down and coming up with a mechanism behind this. Okay? It is purely based on a lab result. Is that your final product?
No.
Why is it not the final product?
Oxygen doesn't want to be charged.
Oxygen doesn't want to be charged. How does it fix that?
Kicks out the hydrogen.
Kicks out the hydrogen, and we end up with a final product. Several aspects come out of this that are nice. Number one, we notice that we end up with the trans product. So this supports the bromonium intermediate. Take it a step further. We notice that the OH goes on the most substituted position. What does that mean?
It's the
Water had to attack the most substituted position, which means the mechanism that we've got shown in red is our correct one. The one in blue did not happen. How do we know? Tested in the lab. With the previous case of the two bromines, or just bromine and DCM, okay, we have no way of confirming, okay, whether that was attacking the least sterically hindered or the most sterically hindered spot. There is no way to test that. We can test it here as soon as we change that nucleophile. Okay. And what we end up doing is assuming that change in nucleophile didn't change anything else behind the mechanism, and we still end up with our final result. We still end up with an enantiomer, because it is still an achiral starting material. Okay. We still end up with the trans or anti-addition. But the more important part is to note where the nucleophile substituted, okay, or where the nucleophile attacked. It attacked at that most sterically hindered position. What happens if I change the nucleophile now from being water to an alcohol, HOR? Is that going to change anything? I kind of like the no answer. What does it change? Sorry for that outburst. Our net result with our OR is instead of having OH, we have OR. That's all that it changes. Okay. We've seen this before. We talked about what happens when you change your nucleophile. Okay. All that's exchanging is we're now switching that around. We now have OR. We still have the trans product. We still have the anti-addition. Okay. But now instead of there being a hydrogen and having an alcohol, we have what functional group? An ether. Okay. So within that mechanism, are you responsible for the mechanism? Kind of, sort of. What you are responsible for recognizing is that your product here from this reaction is an anti-addition. You're responsible for the regiochemistry. Okay. Bromine at least substituted, and our nucleophile at most substituted. Okay. So you either understand the mechanism or you start memorizing all of those aspects. Okay. You may think that this is now a drastically different reaction than we ran before. It's ultimately the exact same as the acid-base reaction that we did in chapter 11. The only thing that is different is that we are now forcing the anti-addition. Think back to the acid-base reaction. What happened when we added acid? Where did the hydrogen go? Went there, and our chloride went there. So our positively charged atom always goes to the least substituted location. So instead of referring to Markovnikov and anti-Markovnikov, you can instead focus on the charges that come out of those atoms. Where it becomes weird, in this case, is bromine. We would typically classify as what charge of an atom? Negative. But that's when we're thinking about bromide. Bromine, the element, is either 0 or positive. Okay? So our positively charged atom goes to the exact same location. The only thing that is different about chapter 12 is that we are forced into this anti-addition when we're talking about the bromine reaction. Okay? Most of the reactions that we look, well, that's not quite true. A lot of them are anti-additions. Questions with those reagents? How about the last one? So since I heard someone mumble that off, what is PT, PD, or rainy nickel?
Metals.
Those are all metals, and they are all metal catalysts to help facilitate this reaction. Any ideas as a guess of what might be happening? What do we expect for a product? We're just adding hydrogen. Exactly right. So there's our product. Okay. That's it. All we've done is added hydrogen across the double bond. This reaction is a little bit different, though. Why might this reaction be different from our bromine reaction?
Because it's not as big, and so it doesn't matter.
So we could potentially run the same parallels that we're saying hydrogen acts as, okay, an electrophile. It's a little bit questionable because in the case of bromine, why did the bromine act as an electrophile? It was attached to an electronegative element that could take the electrons away. Is hydrogen particularly electronegative? No. So that's a pretty questionable first step. Okay, but let's just go ahead and say that's fine. That means we're then going to have to break a bond, right? But we also have to form the other bond. What do I form that other bond with? What electron source? There is no electron source. Okay? We potentially have that sigma bond, but that sigma bond now needs to break. How can I get all of this to occur at the same time? Okay? At best, if I went through and did this, I end up generating H+. So at best, what we're saying is that those electrons would come from there to form that. Which then means, what else do we have floating around? H plus. We also have 2 bonds on a hydrogen, which doesn't make sense. So nothing about this seems to make sense. It doesn't match our standard mechanism. We don't have it as an acidic first step, so we're running into problems. How is that problem alleviated? That's what your metal catalyst is for. Okay? What your platinum, palladium, or your nickel are doing. What those surfaces are providing is now a way to interact with their metal surface, and on the metal surface you have metallic bonds, which means you have a sea of electrons. That sea of electrons can coordinate, meaning it will grab both the pi bond and elemental hydrogen and stick it to the surface. The result is that our pi bond becomes coordinated to our platinum surface. And our hydrogen becomes coordinated to the platinum surface. What is that going to do about the dynamics of the reaction? Say that again?
Put them on the same plane.
The hydrogens get added across the double bond on the same plane. Which means if I were to draw in my hydrogens, there's one, where's the other? It's also going to be wedged. They must get added on the same plane, and that's because of that surface contact with the platinum. Which means, what type of addition do we have here? I see.
Sin.
We have a syn addition. Was it particularly relevant for this molecule? Why are you saying no?
I don't see anything special about it. We could have done it.
What are you looking for something special? What do you mean? Stereocenters. There's no stereocenters in the product. All right, that's going to be one of our big signifiers on this. The other thing is there's no cis-trans relationship either. If I had added on, say, another methyl group, we could now be looking at the relationship between those methyl groups. That could potentially further complicate things, whether it's syn or cis or trans, syn or anti-additions. Without that material, we have nothing to evaluate. Right? So what you're evaluating is really just how does that hydrogen add across the double bond. As far as these hydrogen additions go, they are always added on the same side. That is what the platinum catalyst is there for, to force the hydrogens on the same side, because the hydrogens cannot form that 3-membered intermediate.
Can you explain what you electrons on platinum or palladium?
Sorta, kinda.
What exactly, it's just a sea of electrons, wouldn't it repel any electrons coming from the pi bond there? I mean,
So as a sea of electrons, those electrons are constantly moving, and you can open up holes where you can coordinate more electrons into it.
do you mean metaphorical sea of electrons, or is it?
Well, it depends on your definition of a metallic bond. So there are those that postulate that the metallic bond is a sea of electrons, meaning the electrons on one platinum can constantly move to any other platinum within that surface. Okay? There is also another theory where the metallic bond just means that the electrons bump each other very readily, and so if we push electrons in on one side, another electron pops out on the other. Okay, so you end up doing a sequence of redox reactions as opposed to just moving electrons through it. Okay. It has to do with inorganic chemistry, which, if we're going to be honest. That type of reaction is what is known as what kind of a reaction? It's a redox reaction. So we're going to real quickly kind of whip through this. We're looking at oxidation and reduction, which you'll notice is not in Chapter 12, is actually in Chapter 19.5. Did I write it up there? I did. Chapter 19, Section 5. That is the only section out of Chapter 19 that you need to be looking at before the final. Okay. I will try to make a homework assignment on that just to give you some extra practice on it, but it's not that much extra. What you're really looking at is that syn addition is our primary characteristic of this. What's happening in our redox reaction? Reduction, gain of electrons, oxidation, loss of electrons. So if we take a look at this reaction, the alkene plus hydrogen to just our alkane, how do we know that was redox? How would you figure out it was redox in Gen Chem? Or summer, something I like a little better. You could look at oxidation states for all of the atoms and look to see what atoms change their oxidation states. The rule of thumb that gets you there a little bit faster, find anything in its elemental state. Once you've found that, what's its oxidation state? 0. When we look at it in a product, can its oxidation state be 0 again? No, it must have changed, which means you are looking at redox. What is the oxidation state for hydrogen in most compounds? +1. We went from a 0 to +1, which means the hydrogen was oxidized because it lost electrons. This is where it gets weird. This reaction we refer to as reduction. Why do we refer to this reaction only as reduction?
Because the ring was reduced.
It is by definition a redox. Both must happen. Hydrogen was oxidized. Why do I call it reduction? What was this class? Organic chemistry. What happened to the organic molecule if hydrogen was oxidized? The organic molecule was reduced. That's why we refer to it as a reduction reaction. Okay? So we get a slight spin on referencing our redox reactions in OChem because all we care about is the organic molecule. So in this case, this is solely a reduction reaction. What if we did the reverse? It's now an oxidation. Okay? We'll pick up there on Wednesday. Hopefully I'll stop deleting all my written work.